Hello. Yes, can you hear me first of all?
Yeah.
Okay, perfect. Then let me know if you see them.
Yeah, it's clear in full screen.
Okay, perfect. So first of all, thank you very much to the organizers to allowing me to give this talk, which I'm really happy to give. Well, you all have known about the anomalies, okay, a lot for this conference, of course, and also during this conference, mostly from the theory side. So I'm going to try to give an experimental overview, focusing on the latest results, but also trying to show the coherence of the pattern and essentially where we are now in comparison with the standard model. So first of all, a quick reminder. So we are talking about the study of decays, and this implies some direct searches for beyond the standard model physics. And this is complementary to direct searches for new particles, and it allows us to access effects from potentially large mass beyond the standard model physics. Now, since 2013, we have been seeing a coherent pattern of anomalies in PDKs. And something really interesting about them is that they are flavor dependent, and this may connect with the flavor puzzle, which would be amazing because it could actually give us a way to understand what is beyond flavor in the standard model. So I will talk quickly here about which are the main experiments involved. So we have two categories, let's say. First of all, the Hadron machines, so the Large Hadron Collider with LHCb, Atlas, and CMS. And here we will be talking about large production rates for the different species, so large statistics, and also access to all the B-Hadron species. Now, in the B factories, we will have less statistics, but the good point is that we are talking about electron-positron colliders, and the environments will be cleaner and the analysis easier in many of the systems. And here we have Bell and Bavar. And also, Bell2 is an experiment which is currently ongoing and has huge potential. I'm not going to cover results from it though, since they are still accumulating data, but you are welcome to check several contributions to this workshop on prospects for Bell2 and measurements. Now, for the LHC, I will also focus mostly on the LHCb experiment, which is focused on the study of flavor and has very good PID and vertexing capabilities. So talking about the LHC experiments, here I am briefly showing the detectors for LHCb, CMS, and Atlas. And in general, I will be talking to analysis done with run 1 and run 2. Run 1 refers to the data set collected up to the year 2012 at the LHC, while run 2 is the one collected from 2015 to 2018. Now, this is the map of the anomalies, and I'm going to try to go through the different regions and show how this is connected. So first of all, we can differentiate two big separate regions. One of them is that of neutral currents. The other one is that of charged currents. Now, in neutral currents, we are talking about B2SLL semi-leptonic decays, where L is a lepton, and we will be talking mostly about muons. And these are decays which are suppressed, very suppressed in the standard model, which means that new physics contributions that may not be suppressed can actually have sizable effects. Now, the other region is that of charged currents, and here we have B2C tau nu, and here we will be talking about mostly tauons. And the difference is that we are talking about tree-level decays in the standard model, hence large statistics, clean standard model predictions. So it's a very different system. Now, I will be mostly focusing on results. If you want to know the details of the analysis, specifically for neutral currents, please see the synchronous talk by Jacopo Cerasoli. So let's go to these results, starting with neutral currents. And it has already been pointed out in the conference that there are several measurements in this system, none of which is shows an extreme tension with the standard model, but many of them show tensions. And a crucial point is that actually we can combine them. The way to do so is through effective field theories. Specifically, they can be constructed at the de Hadron energy scale. And this means that there is a finite set of operators and multiplicative Wilson coefficients that allow to describe all the amplitudes for these modes in the standard model or beyond. So the goal is to measure these coefficients in different decays in a complementary way, and to test the differences with the standard model predictions. And just to say that this effective field theory is completely analogous to the 4-point interaction of the beta decay. So let's go to the measurements themselves. I will start with leptonic, fully leptonic BDKs, and with measurements of branching fractions. So here the most famous one is the decay of BS to mu mu and B0 to mu mu. Here we are talking about a very rare decay in the standard model, and it is sensitive to the so-called C10 Wilson coefficient. And this is territory of the LHC in the sense of having measurements from ATLAS, CMS, and LHCb. Here you can see the latest measurements from ATLAS and CMS. You see that ATLAS is close to observe the BS to mu mu decay, while CMS has observed it. And on top of that, also measure the effective lifetime of this mode. Now I'm going to show you the latest measurement from the LHCb experiment. And here we have a lot of statistics. And BS to mu mu is observed with more than 10 sigma. And the measurement is about 10% below the standard model prediction. If one combines this measurement with the ones from the other experiments, the tension from the standard model is about 2 sigma in this case. LHCb has also updated the measurement of the effective lifetime for this decay. And this one is so far compatible with the standard model. It will improve with more statistics. Now let's move on to semi-leptonic decays, still in neutral currents. And here we will have that there is a dependency phenomenologically on a variable which is Q squared, which is the dilepton invariant mass. And as a function of this variable, we will have sensitivity to different Wilson coefficients. Now, there are 2 peaks that you can see here, which are resonances, specifically J psi and psi 2s. And in these regions, they will be vetoed in analysis or used as control samples because they are resonant modes 3 level and hence assumed to be standard model-like. There are 3 types of measurements that we are performing, and they have different levels of theoretical uncertainty. The first of them is that of branching fractions, and this has relatively large uncertainties that are coming from form factors or the so-called charm loop effect. We can go to a bit more complicated analysis experimentally, but cleaner theoretically, which are those of angular observables. And here we essentially can cancel most of the uncertainty for form factors, but still have some contribution from the charm loops. And then finally, we have measurements of lepton flavor universality ratios, where we can cancel up to very good point these uncertainties, and they are very clean theoretically. So let's start with branching fractions. And I'm going to show you a summary of some measurements of some leptonic decays with muons, 2 muons in the final state. These are previous measurements, and this is the branching fraction as a function of Q squared. And you can see that there are measurements from different experiments, but mostly from LHCb. And you can see that there is a systematic overestimation of the standard model prediction for these branching fractions at low Q squared with respect to the data. Now, I'm going to show you the latest measurement from LHCb in this field, which is that of the branching fraction of the BS to 5 mu mu decay. This is an analysis that uses the full round 1 and round 2 data set, and it's an update with respect to a previous analysis from LHCb. And then the previous analysis was showing a tension of 3 sigma with the standard model. In this case, the found central value is consistent with the previous one, and the uncertainty is reduced by a factor 2. And here we are talking about a tension with the standard model, which is at the level of 3.6 sigma, which happens to be the largest tension so far. Now let's go to something a bit cleaner theoretically, which is the measurement of angular observables. And here, instead of integrated branching fractions or only as a function of Q², we will be further splitting the differential decay rates and look it as a function of the angles. So for example, you can see here the distribution, the angular distribution for the decay B0 to K star 0 mu mu with different colored coefficients. And these coefficients are combinations of Wilson coefficients that we want to measure and form factors that carry acoustic uncertainty. Now, one can take smarter observables like P5 prime, the famous P5 prime that takes ratios or combinations of these observables, which cancel to a good point the uncertainty coming from form factors. Now, I'm going to show you here a set of previous measurements of P5 prime in the decay mode B0 to K star 0 mu mu. From different experiments with LHCb still having the most precise one. And you can see that at low Q², we see tensions with the standard model at the level of 3 sigma. So these are two very recent measurements of a mode which is not B0 to K star 0 mu mu, but the charge conjugate, which is B plus to K star plus mu mu. The first measurement is from LHCb. And it's an update with full run 1 and run 2 data. And this is the first full angular analysis of this mode. The tension with the standard model here is about 3 sigma, and it is really interesting to see that this is fully consistent with the neutral mode while they are very different from each other. There is another measurement from CMS, also in the same mode. This one is not a full angular analysis. It has a restricted number of observables and it's using only 2012 data. So it's still dominated by statistical uncertainty, and with more data can give better results even in this mode. Now, the latest measurement of this kind of observables is this one, is the angular analysis of VS to 5 mu mu that is shown for the first time this week. This is an update with full run 1, run 2 data, and there is a significant improvement in precision with the previous LHCb run 1 analysis. You can see here on the left a plot of the invariant mass, and on the right a plot of how one of the observables, longitudinal polarization fraction, changes as a function of Q². And in this mode, one can measure CP averaged angular coefficients like the previous one, like this FL, but also CPA symmetries. The CPA symmetries have been found to be compatible with the standard model so far, given the statistics available. But FL shows a slight tension with the standard model, and if one computes this tension as a function of the value of the C9 Wilson coefficients, one finds a tension of about 1.9 sigma. Now let's move on to the cleanest type of observables in semi-lepton decays, and this is the case of the lepton-Flavin universality ratios. So they have been introduced already before in the conference, and we will be talking about ratios of muons versus electrons in this case, and ratios of the form of RK, for example, where we have the ratio of branching fractions of B to K mu mu, and the same for electrons, B to K EE. The standard model predictions for them are to be one with very good theoretical uncertainty, and experimentally these are measurements which are easier for the B factories because they reconstruct with similar qualities, say muons and electrons. Why for LHCb? The electrons radiate significantly through Bremsstrahlung, and this impacts the resolutions and the efficiency for electrons that are worse as for muons. So in order to take this into account, what is done experimentally is to take the double ratio of B to K mu mu rare mode over the same with the resonant mode, which should be standard model like, and this cancels the ratio of efficiencies, and then take another an extra ratio with the modes for electrons, where again the efficiencies can cancel up to good points. So this is a very clean also experimental measurement. And in order to prove further how well we reconstruct electrons, what is done is to measure as a cross-check the single ratio of the B to K J psi over B2KEE, so the resonant modes, because this is supposed to be 1, because it should be a standard model like, and it is found to be 1 in the cross-check, also as a function of kinematics. And one can also measure the double ratio, but at a different point in Q-square, which is that of the resonant psi2s, which is also expected to be 1, and it's also found to be 1. And you can see here on the right, 2 plots of invariant mass for the rare modes, on top for muons, on the bottom for electrons. So let's talk about the result. The result is 3.1 sigma away from the standard model prediction. And this is a milestone because it is the first measurement of a lepton flavor universality observable. Again, very clean, that passes the level of 3 sigma. And here, the uncertainty is dominated by statistics, so it will reduce over time. And one could still be tempted to say, okay, maybe there is a problem with the electrons in LHCb because of the reconstruction. But actually, if one translates this ratio in terms of absolute branching fractions, the anomalous one is that of the muons, which is consistent with the previous measurements of branching fractions and angular observables, again, for the muons. Now, not only RK, we have also measured in LHCb RK star, which deviates from the standard model the level of about 2.5 sigma, 2 beams in Q square, and also RPK, which has larger uncertainty, but deviates about 1 sigma. Now, at the B factories at Bell, they have also performed recent measurements of both RK and RK star, still with larger uncertainties in comparison to LHCb, and the results are essentially consistent with LHCb and the standard model. So this needs a bit more statistics to have similar sensitivity. And now we can leave apart for a while the neutral currents and go to the charged currents. And here we will talk about semi-leptonic decays and lepton flavor universality ratios. So in this case, we will have the well-known RD and RD star. So RD is similar to RK, but here we have B going to D tau nu over B going to D mu nu, or E mu. In this case, the muons and electrons can be considered at the same level, while the tauons are the ones that are being studied. So these are 3-level transitions in the standard model. So we have very large data samples and they are theoretically clean. Experimentally, though, they are pretty complicated because we have neutrinos in the final states, so partial reconstruction. And this is much easier to do at the B factories because they have a coherent production of B bar pairs, hence they can put constraint, they can know the total momentum of the signal and hence put constraints on the kinematics, so have good resolutions. While in LHCb, we cannot do this, and instead we need to use some kinematic approximations to know the momentum of these particles. And we can at least profit from the known flight direction of these particles through very good vertexing capabilities. And we can also use isolation tools to remove extra tracks or neutrals around the signal. So I'm going to comment on the LHCb measurements of RD star. We have 2 of them, which are very complementary because they focus on different decays of the tauon. First of them is the muonic one with a tension with the standard model at the level of 2.1 sigma. And the other one has a hadronic reconstruction of the tau, and this one has a deviation of 1 sigma with the standard model. Now, this analysis only used round 1 data, so they are still being updated while we are talking. And the statistical and systematic uncertainties are similar in size, but most of the systematic uncertainties are data-driven, so they will also scale down with more data. Now, Bell has also recently measured, has a recent measurement of RD and RD star together. This is the most precise measurement of the system up to date, and the result is at the level of 1.2 sigma above the standard model. Now, one point is that at the B factories, they have typically averaged the denominator on muons and electrons, while now there is theoretical interest, given the anomalies with muons, to split these ratios on tau versus mu and tau versus E. At LHCb, we only do it with muons because it's much easier for us than electrons. Now, talking about the combination, you can see here the combination for RD, RD star. the world average in red compared with the cross, which is the standard model, and the tension is at the level of 3.1 sigma. And on top of this, the LHCb has also measured a ratio RJ psi, which is also 1.8 sigma above the standard model. Now, even if the tensions differ from measurement to measurement, one crucial point is that here, every single measurement is above the standard model predictions. Now, how do all these things play along together? So this is, for illustration, a list of anomalies, just some cherry picking of them. So what is one supposed to do with all these measurements? How can they be combined? Well, this is what is done in global fits that have already been introduced in this conference in several occasions. And historically, these global fits were done in B2SLL, in the B2SLL system, and they are finding big tensions related to some specific combinations of the C9 and C10 Wilson coefficients. But also recently, in the last years, there have been some proposals that there can be a very good phenomenological theoretical interplay between B2SLL and B2C tau nu. And there are models that combine the anomalies in the two systems. Now, these global fits are really good because they motivate specific models that can be tested experimentally, and they offer complementary measurements. And these models can be, for example, including leptoquarks, Z primes, and some of the measurements can be direct searches for these extra mediators, for example, at Atlas or CMS, or also precision measurements of other PDKs that like lepton flavor violating modes, B2S tau-tau transitions, etc. Now, these global fits are extremely useful because of this model study, but also one would like to know at some point, okay, what is the actual tension of the measurements with the standard model hypothesis? Would anyone be able to claim a discovery? And there are discussions in the community in this sense. How can one estimate somehow a global tension? And for example, there is a very recent paper from these authors that estimates or proposes a method to estimate a global significance of the new physics hypothesis versus the standard model, restricting to B2SLL case, and they include somehow the Lucas-Ware effect, and using clean measurements only, they found a tension of about 3.9 sigma with the latest measurements in this system. Now, as conclusions, the pattern of anomalies in BDKs that have been found since 2013 is coherent and doesn't go away. New measurements seem to reinforce it. We have reached a milestone with the lepton flavor universality measurement of RK, because it has passed for the first time 3 sigma. And significantly larger tensions with the standard model are found when several measurements are combined. Now, as prospects, I have shown many analyses that already have the full round 1 and round 2 dataset analyzed, but there are still many of them that will be released because they will be improved with more data, or we will do some complementary measurements. Then round 3 at the LHC will start next year with 5 times the instantaneous luminosity at LHCb. BEL2 is entering the game and will collect 50 times the statistics of the B factories, and then the high luminosity LHC will increase the current data set by a factor of 100. So that was it. Thank you very much for your attention, and stay tuned.
Thanks a lot, Julian, for the very clear and comprehensive overview of these anomalies. I once again invite people to enter their questions into the chat. We have one already, which is somebody asking for clarification of what NP stands for. And I guess that's new physics, but maybe you can give some more information about what these new physics models might include.
So indeed, it is it's a bit of jargon. We're talking about beyond the standard model physics, and there are different models with different mediators that try to explain these anomalies. Some of the most trendy ones now are leptoquarks because of the capacity, for example, to explain altogether the anomalies in B2SLL and B2C tau nu. So they are receiving a lot of attention, but also, for example, Z prime is a possibility to explain B2SLL. So there are also many models in that sense. But yeah, there is a plethora of models in this sense that try to fit all this all together. And the good point is that indeed all the global fits and with the different models, they really find coherent pattern and very big tensions with the standard model along these Wilson coefficients.
Okay, thanks. And I guess while we're on this topic, somebody has asked, what is your favorite BSN extension to explain these anomalies?
Well, I mean, that's a personal thing, definitely at this point. There's no way to say. I mean, I'm particularly mostly involved in the case with tau, so I am fully in for leptoquarks. I mean, there is this interplay that I briefly commented about the connection between the two anomalies. And these models, for example, predict some big contribution of beyond the standard model physics for the third family, and then small contribution to the others, to the second one, but also through radiative effects coming from the third family, they can actually give a better explanation even of the anomalies in B2SLL. So these seem to be pretty promising, but that's a personal preference.
Thanks. And then we have one more on slide 10. It says you show a new result with the phi region shaded. Is the measured branching fraction of BS to phi with phi to mu mu compatible with that of phi to KK?
That of phi to KK.
I'm not sure I understood.
So in principle here, one tries to restrict themselves to the regions without the resonances because they are standard model like. Phi is another resonance on top of J psi psi 2s, so should be vetoed. But I don't understand the question further than that. The beams are focused on the regions where the rare decays should live. And there was also the comment yesterday, I think to Guy Wilkinson in another plenary talk about the high Q-square beams, like why they are not measured. In that case, it was out of experimental difficulties in this region, although they are being studied right now. So the beam in any case tries to maximize the sensitivity to new physics.
Yeah, thanks. I'm not completely sure I understood the question either, but they can perhaps clarify while you're on this slide. I was kind of curious to know, as you mentioned earlier in the branching fraction measurements and the angular analyses, there's different sources of uncertainty. When these global fits are done, is there a straightforward way to combine the branching fraction and angular analyses?
It depends strongly on the fit itself. Depends on the authors. There are fits that try to include everything. There are fits that try to focus on clean observables. I may comment maybe very quickly on this specific one. So this is not a global fit per se. It's a study with an ensemble of sieve experiments, which tries to be very conservative And for example, this one is only using lepton flavor universality measurements. And if I remember correctly, it also includes some angular observables, but actually marginalizing out completely everything that could that has a big uncertainty on the standard model, specifically the charm loop effect, which is something that is very controversial in the theory community. So even if some people are very confident that it is well measured, here they took a very conservative approach of completely removing that part of information. So this is kind of with the least questionable inputs theoretically, and even then the significance is 3.9. Then different global fits choose what to include, and the tensions vary strongly.
Right. Okay, thanks.